selecting weights. We introduce these incentives by adapting the inflation mechanisms with a speculation-based reward in the form of bonds B. Here, B is the proportion to the bonds owned by a peer. Bonds accumulate at each step, similarly to token inflation, where B equals W. In this way, peers accumulate bonds in the peers they rank us, thus bonding themselves to those that they are connected to. Using the B bond matrix, the chain redistributes the normal incentive scores like market-based speculation on traditional equities. The peers that have accumulated bonds in peers that others will later value attain increased inflation themselves. Thus, it makes sense for peers to accumulate bonds in peers, which it expects to do well, according to other peers with stake in the system, thus speculating on their future value. Finally, we adapt this mechanism slightly to ensure peers attain a fixed proportion of their personal inflation. For instance, 50% becomes the mechanism step update, which determines network incentives across the N peers. The incentive function in section 2 rewards highly trusted peers. However, it may not solve the collusion problem. If the honest nodes do not reach consensus, notably, loose, unused stake or incorrectly set weights will detract from the inflation proportion of honest peers in comparison to a colluding subnetwork. The honest network, although holding more stake, may not gain enough inflation to overshadow its adversary. The dishonest subgraph need only attain enough inflation to compete with its largest competitor, not to entirely dominate the network. This attack is possible when the majority of token inflation is being distributed towards peers which are non-majority trusted in the graph. The chain can measure this through the through a loss term. The term is negative if the majority of inflation is being distributed towards peers with more than zero point 0.5 consensus. The chain uses the loss calculation as a peg. By increasing the number of weights the average miner sets across the network, the chain can ensure consensus. The network the left network has low consensus. The system is not resistant to a cabal with less than 50% of the stake. The chain increases the number of edges set by peers. At this point, the majority of inflation flows to peers with majority consensus. The steps to set to run a peer in the network. The peer defines its data set. At each training iteration, the peer conditionally broadcasts batches of examples from D to its peers X equals batch size, sequence length, input. Okay. The responses F equals blah blah blah. Each of the common shapes FIX, batch size, sequence length, output are joined using the gating function and used as input to the local model. Comparison against the target labels produces a loss gradient which backpropagates through FI and out to the network. During 2 and 3, the peers learn the weights of their row by measuring the value of the signals produced by their peers. At distinct time step T, participants submit changes to the weights to update the ranking R, inflation I, consensus terms C, and bond distributions B. The chain measures loss and optionally distributes newly minted stake into this network S. According to the bond ownership tensor standardization, a common encoding of inputs and outputs is required for the various model types and input types to interact. The use of tensor modalities can be used to partition the network into disjoint graphs. At the beginning, the network can be seeded with a single modality, text, then expanded to include image, speech, and tensor. Eventually, combinations of these modalities can be added, for instance, text image, to bridge the network into multimodality landscape. Incentives to connect modalities can be integrated with the same trust scaling suggested in section 2. Eventually, successful models should accept inputs from any modality and process them into a useful representation. For consistency, we can use a standard output shape across the network: batch size, sequence, dim, output, dim, similar to the common tensor shapes produced by language and image models. By working on abstract input classes, we can ensure participants work towards a general multitask understanding. Participants may use completely distinct computing substrates, dataset, LAMPL, blah, 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 models and strategies for maximizing their incentives in the market. It makes sense for peers to work on unsupervised data sets where data is cheap and privacy not required. Conditional computation: as the network grows, outward bandwidth is likely to become a major bottleneck. The need to reduce network transfer and a method of selecting peers is required. Conditional computation can be used where peers learn through gradient descent how to learn and prune neighbors in the network. For example, a key product key layer or a sparsely gated layer. The conditional layer determines a sparse combination of peers to query for each example and multiplicatively rejoins them, cutting outward bandwidth by querying only a subset of peers for each example. The method can be drastically increase output bandwidth, allowing peers to communicate with many more neighbors in the graph. In essence, the layer acts as a trainable DNS lookup for peers based on inputs. Furthermore, being trainable with respect to the loss, it provides a useful proxy for the weights. Dependence between functions ensures that models must stay online and cannot be run in production. Breaking this dependence can be achieved using distillation, Hinton et al., a compression and knowledge extraction technique in which a smaller model, the student, mimics the behavior of the remaining network. The distillation layer is employed in conjunction with a conditional computation layer where the student model learns to mimic the network using the cross entropy between the logits produced by the gating network and the student's prediction distribution. Hey, dickhead, get your mind right. Don't preach to me about my perky habit, bitch, this is my life. Because the distilled model acts as a proxy for the network, models can be fully taken offline and evaluated. Recursion through the network is also cut between components, allowing for arbitrary network graphs. If models go offline, their peers could use the distilled versions in place. Private data 6 can be validated over the distilled models instead of querying the network. Eventually, components can fully disconnect from the network using the distilled models to do validation. Yep, this sounds like the DeepSeek story, he says. our goal is to our goal in this work is the production of ranking R equals Ri over peers, where the score R represents a participant's information theoretic significance to the benchmark. Following Lacoon and Lacoon et al., Ute et al., is it is reasonable to define this significance by equating it with the cost of removing each peer from the network. We can derive this score analytically. Fxi is a perturbation
Perturbation.
perturbation of the jth peers input with the ith peers is removed from the network. Yo, creative, what's up, dude? 777. You must expect great things of yourself before you can do them. MJ, the GOAT, bro. Note, when the error function QJ is the twice differentiable cross entropy, the HQJ is its Fisher information matrix. And RI is suitably measured as each peer's information significance to the network as a whole. However, information theoretic weights require the full Heisen of the error. In practice, it is more reasonable to use heuristic to propagate a contribution score from the error function through to the inputs u et al. For instance, weights from the gating layer section 6 provide a useful differential proxy collusion. We consider the scenario where a subnet of peers in the network have formed a cabal, a set of colluding peers attempting to maximize their inflation without accurately scoring their neighbors. The fight between the honest graph A and the stake SA and the disjoint cabal with stake B can be determined by the proportion of network stake held by each. The honest graph must attain more information to maintain its dominance, protect the network. We assume that the proportion of stake in the honest graph is more than that found in the dishonest graph, and that the chain has reached consensus. Since all peers in B are disjoint from A, our loss term is positive because L is under O. It must be the case that RA is under O. 0 is negative, and there are peers in the honest subgraph who are connected to the majority. As the chain progresses, newly minted stake is being emitted to our inflation rate T or R in proportion to I equals R times T. Importantly, the gradient of the incentive function with respect to the stake is positive and superlinear at our inflection point between the honest and dishonest graph. Notably, this ensures that the amount of stake held by each subgraph reflects on a non-linear change in their inflation at the next iteration. Initially, since SA is over 0.5 and SB is under 0.5, the proportion of stake emitted in subgraph A exceeds that in subgraph B, and subgraph A's incentive grows superlinearly compared to B. The result is that the ratio stake SB over SA and B decreases. The cabal must continually add stake to its subgraph to maintain over time. We consider this proportion between the competing graphs under continuous inflation, converting to Python code. Conclusion, we have proposed an intelligence market that runs on a P2P network outside of a trusted environment. Crucially, the benchmark measures performance as representational knowledge production using other intelligence systems to determine its value. The fact that this can be done in a collaborative and high resolution manner suggests that the benchmark could provide a better reward mechanism for the field in general. To achieve this aim, the paper began with the definition of a P2P network composed of abstractly defined intelligence models. We showed how this framework allowed us to produce a ranking for each peer based on the cost to prune it from the network. Peers negotiated this score using a set of weights on a digital ledger. However, the system was incomplete without mechanisms that prevent participants from forming dishonest graphs. To resolve this, we propose an incentive scheme based on peer connectivity, which exponentially rewarded peers for being trusted by a large portion of the network. This ensured that over time, dishonest subgraphs decay to irrelevance. Following this, we showed 1. how peers reduce the network bandwidth by learning connectivity using a differential layer. And two, they could extract fully network disconnected machine learning models to run in production. The result is an intelligence market that rewards participants for producing knowledge and making it available to new learners in the system. Fire, bro. Yo, why is everything called at all? I don't know. Super PvP, damn. Why is everything called at all? I don't know. I think that's like saying something to bit tensor mining plan here. Let's go ahead and check this out, dude. Thank you, Kyler, for spinning this up. Don't hack me, bro. I'm over here downloading stuff, downloading stuff off the internet. Kyler's my boy, though. BitTensor mining plan, a comprehensive plan. Thank you, Kyler. Here's a detailed plan for exploring BitTensor mining, including a profitability analysis and a step-by-step project plan. Understanding BitTensor mining from the video and research core concept. BitTensor is a decentralized network that incentivizes machine learning and other specialized tasks through a cryptocurrency called Tau. Unlike Bitcoin mining, pure computational brute force, BitTensor mining is useful work contributing to various subnets. Key players, miners, perform the specialized work required by a specific subnet, running AI models, storing data, making predictions. They compete for rewards. Validators check the work of miners, ensuring accuracy and value. They also earn rewards. Subnets, independent networks with BitTensor, each focused on a particular task, e.g., storage, price prediction, advertising, AI. Each has its own rules, requirements, and reward structure. Competition. Mining is highly competitive. Miners constantly strive to improve performance, code optimization, better hardware, unique data to earn more rewards. Tau token, the native currency on the BitTensor network. Deductive reasoning and profitability. This section assesses the viability of BitTensor mining as a business opportunity using deductive reasoning and considering real world cases. Premise one, demand for decentralized services. There's a growing demand for decentralized alternatives to centralized services, cloud computing, AI, data storage, due to concerns of censorship and data privacy. Premise two, BitTensor provides a framework for decentralized services. BitTensor's subnet structure allows for specialized decentralized networks offering these services. Incentivization drives participation. The Tau token financially incentivizes miners and validators, ensuring the network operation and growth. Premise four, competition drives innovation and efficiency. Absolutely. Conclusion, if the demand for decentralized services continues to grow and BitTensor attracts and retains skilled developers and miners, then there's a strong potential for profitable mining. Real world use cases, AI subnets.
Choice, right? You just decide what it's going to be, who you're going to be, how you're going to do it. Just decide. And then from that point, the universe is going to get out your way. It's like it's water. It wants to move and